Talk to you about today are things called Ferris wheels. Ferris wheels, you probably know what these are, right?
Yeah.
Well, Ferris wheels typically do this. You have a big wheel, and you know something about the wheel. Maybe you know the diameter of the wheel is, I don't know, let's pretend it's 40 feet, okay? And then maybe the Ferris wheel itself is a certain distance above the ground. So let's say it's 5 feet above the ground. Okay? And then what happens is that you get on. So you get on here. We'll call this the point where time is equal to 0. And then it starts to rotate. So you need to know some things. So let's pretend the Ferris wheel rotates in this direction. Okay? And let's pretend that it takes, I don't know, let's just say 8 minutes per revolution. It takes 8 minutes to go all the way around and land back where it started. So those are important facts to know. If we know this, then we can do some pretty good math. So let's state a goal here. What I'd like to do is I would like to create a function. We'll call it h of t, and the function returns as an output my height above the ground after or at time t. That's what I want this function to do. So I want a function where if I say I've been riding this thing for 6 minutes, how far am I above the ground? I've been riding it for 5 minutes, how far am I above the ground? That's the goal here. Okay? All right. So let's take a look. Let's see if we can describe the motion a little bit. What we're going to try and do is, before I actually find a formula for h, I'm going to actually just try and draw a graph of it. I claim we can draw a graph of h pretty easily. All right? So here's t equals 0. And so we could start to label some points right away if we wanted to. So let's make an axis here. Let's call this time. I know it takes 8 minutes to get around, so I'm going to put 8 out here because I know that's when the ride's going to end. And what else do I know? Well, when I get on at t equals 0, I'd be 5 feet above the ground. I'd be this vertical distance that I've drawn in blue. So I'll go up here, I'll call this 5, and I put a dot here. This is the first point on my graph of h of t. Okay. Now, let's go for some easy points first. Let's ask ourselves, how much time went by when I got to the top of this Ferris wheel? So this is t equals 4 minutes. You expect halfway around, half the total revolutions, 8 minutes per revolution. So 4 minutes. And actually, you also know your height at that time. You know that at that time, h of 4 would have to be 45. The 40-foot diameter of the wheel plus the 5 feet that the wheel is above the ground on the bottom. Okay? Here's another interesting point. Here, that's halfway between, that's a quarter of the way around the circle, a quarter of the way around the ride. You'd expect time to be 2 at that point. And h of 2, I don't know it right away, but a little bit of thinking will get it. We know we're halfway up the circle. So we want that green distance plus the blue distance below it. Well, the blue distance below it's 5, and this is just a radius. So it's half of 40, or 20. So now we know that h of 2 is 25. Okay? And then over here, t equals 6 minutes, right? It's another 2 minutes, another quarter from the 4. And again, this height here is going to match the height that was over here. So we expect h of 6 to also equal 25. So now we can get a pretty good sense of what this graph looks like. Here we go. We know we're going to reach a max height of 45. And that's going to happen at 4. We'll put a dot there. We know at 2, we're at a height of 25, halfway between the 5 and the 45. And then we also know at 6, we're at a height of 25. And then at 8, we're at a height of 5. Okay, so there you go. And the question now becomes, how do we connect these things? So, for example, do I just do the following? So let me just copy this graph for a second. Oops, I lost that. Oh, that's how you're going to be. Take this with me to a new page, and we're going to show some different ways that you might try and connect these. So someone might say, oh, I'll just connect it like that. That's what it looks like. Okay? Or someone might say, maybe it's smoother. Maybe it does something like this. Maybe it's the green one. Okay? So our goal is going to be next to find out which one of these things is more reasonable. I'm inclined, it wouldn't matter which one it turned out to be. The red one looks like an upside down absolute value graph, and I know what those equations look like. Right? And then the green one looks like a cosine or a sine curve, so I'm okay with that. All right, so let's consider the Ferris wheel again. There we go. That's not a good picture. Here's the ground. What's that? I keep drawing the wrong thing here. Here's the ground. Here's the Ferris wheel. Here's 5. Okay? And let's consider the following. We know it takes t equals 2 units of time, or 2 minutes to get there. Here's t equals 0. Let's think about where we'd be at t equals 1. So if we, after 1 minute of time, we would have moved halfway along this blue arc. We would have moved right to there. That would have been t equals 1. Okay? Because we're moving at a constant rate of rotation. So let's start to draw some pictures and see if we can't figure a few things out. We know the radius here is 20. Here's the center. There's another 20 here. And then I claim you actually know that distance, because this is another radius. It's 20. And let's state our goal. Let's be careful. Our goal is to find that green height. Okay? So let's draw a little bit more in here. So let's consider that right triangle for a moment. And the reason I'm interested in that right triangle is because I can actually get that whole distance very quickly. I know what that whole distance is. It's a distance from the ground up to the midway point of the circle. So that distance is 25. And then if I could get this distance somehow, this red distance, then I'd be able to do 25 minus this distance. I don't know what this is. I'm going to call it y. If I found 25 minus y, that would be exactly the distance I want. This distance here is 25 minus y. Okay? And this is going to help us find out if this thing is more like a curved graph or more like a straight line or absolute value graph. Okay. Well, we know this angle up here has to be 45 degrees because we're taking an arc. The blue arc is 90 degrees. This side of it has 45 degrees, and this side has 45 degrees. And the central angle and the arc are the same. Okay? So now we're ready. If you look at that red triangle, we can do a little trig. So for example, the sine of 45 equals y, which is the opposite, over the hypotenuse, which is a radius of the circle, which is 20. So y equals 20 sine 45, or 20 times square root of 2 over 2, or 10 rad 2. So now you know what y is, which means that the distance we really want, this green distance here, is going to be 25 minus 10 square root 2. Let's estimate that. So this comes back around 10.9. Now let's go back to our graphs that we were considering for a minute. Okay. On the red graph, when you went to t equals 1, you'd expect this dot to be halfway between 5 and 25. Well, halfway between 5 and 25 is... And that didn't happen. It turned out that at t equals 1, the point was actually lower than that. It was actually right around here, 1 comma 10.9. So this sort of confirms that we should have some kind of curved relationship, right, as we proceed from 0 to 2 minutes. Now, if you were thinking maybe, hey, we're moving at a constant rate of rotation, and therefore it's more likely to be the red graph, here's why that didn't work out. If you think about it, we move a constant rate of rotation, we're moving a certain distance along this arc. Okay? So for this 45 degrees that we've traversed, we've only climbed this much vertical distance. But for this 45 degrees, we've climbed a much larger vertical distance. So we are moving at a constant rate of rotation, and that corresponds to moving a constant distance along the arc, but it doesn't correspond to moving a constant vertical distance because the slope of the circle changes. In other words, if you notice when you're down here in this part of the Ferris wheel, your change in height is very slight as you move forward through time. Your y value of your height is increasing kind of slowly. But then over here, there's a point in the Ferris wheel, and some of you might be familiar with that pit in the stomach feeling you get, right? And the Ferris wheel seems to be climbing very quickly. And that's why you see a relationship that should be more like the green graph. Okay, so now that green graph actually looks like something familiar, doesn't it? Okay, it looks like a trig function, and that's what we're going to stick with. So let's think about some trig functions that we know of. Y equals sine x looks like this. Not quite, right? Y equals cosine of x. There's cosine of x, looks like that. Well, this almost does it. I wish it was flipped, though. So let's do this. Here you go. Negative cosine x. And that's what you have. Okay? So this graph has an equation. It's going to be negative something cosine of x. All right? So that's sort of the first step. And what we'll do tomorrow is we will try to finish this off and find the actual equation. It's not just negative cosine of x. There's some things missing in it. So, for example, it should have h of t equals negative some blank, some number there, cosine of something times t. There's going to be a number there, and then plus another number at the end.